Hello, welcome. So, in the previous episode in this series of creating an FPGA stack machine CPU from scratch, we got the assembler working. And in between episodes, I added a few test cases to the test suite. So now it will basically test all of the instructions that we have implemented so far. I did find a small bug in one of the instructions. That was an issue in the microcode. Let's see. Was it in the microcode or was it in here? It's been a little while. Yeah, it was in the microcode. So it was for the dupe, and I think I had another control signal here. I forget which one, but all that's required to duplicate is just to push. I think I had like nos to toss, like we nos to toss or something like that in there. Yeah, so that's all working. The test program is still in the CPU def. I still need to move it out, but I'll do that later. So we've got testing of drop now. Addition we did last time. Dupe is being tested, and also jumping. So with jumping, that will be very important for today. I'm essentially pushing things onto the stack before and after each jump. And then I jump forward, and then I jump backward, and then I jump forward again. Each time on each side of the jump, I've got push to the stack, and then I verify that the stack has everything that I'm expecting it to. This test is very important because today we're going to implement pipelining, and the number one thing that will break when we implement pipelining is jumps. So this is a very important test. So without further ado, because there is a lot to cover, let's get right into it. One of the things with pipelining is, first of all, the program here is stored in a ROM currently, but it might be stored in an external memory. That memory might have lots of latency on it, and so we need to be able to model that. Furthermore, the microcode might take multiple steps. So we need to be able to tell the fetch unit, hey, we're not ready for more data somehow, right? And also I figured out a way to make this stack machine probably 4 stages. I think we can actually do. But I don't know if we'll get into that in this episode, and I don't want to betray how I'm going to do it. So yeah, the big thing that we're going to focus on today is pipelining the fetch stage and making sure that the fetch stage can handle different kinds of program memories. In my travels, I have found just a few sources that were actually quite good on how to do this. The best source that I've found is this page here. It's fpgacpu.ca. I will leave a link to it in the description, but it's by Charles Eric LaForest. And he basically goes over the ready valid handshake for synchronizing between pipeline stages of something. And we can totally apply this to a CPU as well. So he goes on to talk about interfaces here. So there's 2 interfaces, source and destination. And each one has a valid and a ready signal. The source outputs valid and data and takes ready as an input, and the destination outputs ready and receives valid and data. So that essentially boils down a lot of different schemes. I've seen ready as busy, but then you have to negate it in the logic, and I think it makes it a little bit more convoluted in the end. So I prefer ready rather than busy. I've also seen valid be like strobe or something like that. Again, valid kind of makes more sense as a name to me. It just means the data is currently valid. And we can actually propagate the valid flag through the whole pipeline in order to implement NOPs and things like that. It gives us just one bit that we can set, and then it renders that pipeline stage inert. So that's nice as well. So there's a few rules. One is all signals are synchronous to the rising edge of the clock. We're going to probably push this a little bit, but the big thing is that you can't be changing the valid signal specifically, except at the rising edge of the clock. Ready is a little bit more lenient, although there's a chance we may need to register it, but the pipeline's not going to be very long. So having the ready signal go all the way from the end of the pipeline all the way to the beginning is probably not a problem. Mainly valid needs to make sure that it's registered so that it doesn't change when there is actually valid data. There's also some rules in here around there can be no combinational paths from input to output signals in the source interface. So the ready to valid on the source, if valid goes high, for example, then ready can't go high because of the valid signal going high. You can push that sometimes, but you got to be very careful when you do that. And likewise in the destination interface, ready can't cause valid to go high. That's mainly what it means by combinational paths. Otherwise, you'll get a loop, basically. And it will oscillate in digital, and in the FPGA, it just won't synthesize at all. It'll say, you've got a loop. You got to break the loop. So, yeah. And then this addendum is talking about sometimes you can have a combinational path between them, and specifically from the ready to the ready, or yeah. But you got to be careful. Then it talks about how the handshake actually works. Essentially, when the ready and the valid are high at the same time, then data moves on that interface. So one of the keys to avoiding deadlocks, where does it talk about that? Yeah. One of the keys to avoiding deadlocks and live locks is that valid must go high as soon as there's valid data. You can't wait for a ready signal before putting the valid signal high. And likewise, if the valid signal goes high, it must remain asserted until that data has been consumed. Otherwise, you can get other problems. Basically, it'll go into a live lock where both parties are ready to receive data, but they both miss each other because they're reacting to each other in a loop. So you don't want to do that, and you also don't want a deadlock where data doesn't move at all. So I'd like to implement this as kind of like a circuit that we can use in each pipeline stage. So I'd like to put all of the logic for that in one place. Now, I'm not going to be figuring this out kind of live, so to speak, because the logic is really complicated and it took me a few hours to try and figure it out. So I'm kind of just going to reconstruct it in a way. from something that I've already done. Hopefully that's all right. I'll try and explain it more as I'm doing it. And that'll be easier because I'm not figuring it out as I'm going. So let's just position this window right here. Okay, and edit, go into presentation mode. Okay, so what we need are an input. The input is going to be the source valid signal. And then, by the way, I'm abbreviating just because of the way digital works. If I was doing this in Verilog, I'd just call it source valid instead of svld. I just find that if you have long names for pins, it ends up making your components really big in digital, and it's kind of silly. It would be nice if if there was an option to put the names of pins on the outside of the component, on the wires that are going into it. That would be nice. I think in DigiLogic, that's how I'm going to do it. Just so that there's no pressure to make short names. Anyway, I'm getting distracted and we got a lot to do, so I got to stay on task here. So we have an input on the source side for valid, and we've got an output for ready. So I'm going to say it's source ready because the signal is going to the source. And it just helps to have source on one side and destination on the other side. So there's actually a mirror of this on the other side. We've got an output that is valid. And we've got an input, which is ready. Okay, so you might think, oh, we can just do this and then do this and we're done. But that doesn't end up actually working. So if we just kind of zoom in a little bit and I can show you. What we're going to have is a register. So let me just put the register in here just so we can kind of, I won't have the register in here in the end, but we'll just use it kind of to illustrate what's happening here. We've got data goes in here, and then we're going to need a clock anyway. So we've got our clock, and we've got an enable signal that we'll have to figure out in just a moment. And then we've got our, so this is data, let's just call it S data, and this is destination data. Okay, so the way that the protocol works is if valid and ready are both high at the same time, then data is accepted. So we can represent that with an AND gate, and we can say, let's just move this down. And if they're both valid, then we enable the register and we clock in the data. Or if they're both high, then we clock in the data. So say we've got to change in the data, and things go high here. Nothing happens because valid or ready is not high. And so nothing happens at the rise of the clock. And I'm just pushing a hotkey here to change the clock state. So nothing's happening. If ready goes high, then data is accepted. Now, say this goes low. So the device, the destination is saying, oh, I'm not ready for more data. I can't have more data right now. And then this changes. I guess that totally is working. What is the scenario in which it doesn't work? Because there are scenarios in which this doesn't work. Well, let's say this happens. I think this is it. Yeah. So this is one of the scenarios that we need to handle. The source is saying there's no more valid data, but the destination is ready for more data. And we've got data stored in this register here. The data is totally valid, but we've got valid signal that's low. So we should be able to transfer this data because it's here and it's ready, but valid is low. So we need to figure out a way to handle that situation. So one thing that we could do is we could just put a register on here, just a D flip-flop really. And the D flip-flop will store whether the data was valid last signal or last clock cycle. So then we do this instead. So the destination says, oh, I'm ready for data. The source is ready for data. We clock it. And then now the source has no longer got any data. It needs an extra cycle to read from memory or something like that. Well, we now have valid data here. So the destination knows, okay, I can do stuff with this. And then now there's no more data there. So valid goes low. So that works. Might be better to demonstrate this with another register. So say we've got two registers like this, and we want to know what is the enable signal on this. So you can think of the pipeline stages being this. Actually, I could probably just kind of use one of these. These are a little tricky. Source. How do I build this? Kind of like that. So we've got a source and a destination, and in the middle here, we'd have some sort of logic between the two. The destination, so you can think of this as like the fetch unit, and then the decode stage would be between here, and then you'd have your whatever the unit is after it, your execute stage or whatever you put after it. So then you've got registers between them. How do you know whether you can clock the result here? Well, the way that you know you can clock the result of the computation, and actually I'm just going to put an extra box in here. Let's move this over. So the way that you know you can clock the computation into the destination register is if these two are valid, or these two are high at the same time. So you end up with a AND gate on these as well. And I'm just going to make these maybe 2 bits wide, just so we've got a bit of data. Oh, I need to put some sort of something here so you can see what's here. Oh, 2 bits. Okay, so if you've got data here, it's valid. The destination is ready for it. We clock. So data is in here. It's no longer valid here, but we can accept the data here. So that happens. And then now it's not valid anymore. So then this is no longer active. So that's good. One problem with this scenario, though, is that we've got this register here that is ready to accept data. But because we're relying on the destination to go high before, to say that it's ready before we say that we are ready, we can't clock anything into this register. And that's bad because, well, we are ready. Let's see, why is that bad? It's bad because it can add a cycle of delay, I think. Although I'm not 100% sure on that. But it is bad for some reason. Maybe there's more than one reason, and that's one of them. But we want to be able to accept data when we can. And so we don't want to rely on the destination to signal that it's ready before we accept data. So how do we do that? Well, one thing that we could do is, if we just move this over a little bit, we could add an OR gate here on this line here. So let's just put it there. So we're ready if the other side is ready, or we've got data that we can, or if we are empty and we can accept data right here, right? So the Q naught here basically means that this hasn't been set, and so we haven't accepted any data, and this register essentially is empty at that point. So now when we start up, ready goes high immediately because we have an empty register here that we could clock data into. So let's give it some data and say it's valid. And then when we clock it, then ready goes low because we've got data stored here, but we can't move it here yet. So we can't move it here yet because the destination isn't ready. As soon as the destination is ready, then, well, let's say that this wasn't ready, but let's increase this anyway. We can clock it. Now the destination register here has data in it, and we no longer have valid data here, so we're not saying that the data is valid. And so this will keep the value until we have more valid data. Now, the other scenario to test is to make sure that we can clock every cycle and move data every cycle if we want to. So let's say there's valid data. Data is in the computation stage, it's being worked on. And the destination still has the previous data, but it's ready for more data. So if we clock it again, and let's make sure that we've got new data here. If we clock it again, then data moves from the source into the computation stage. The old data was clocked out, and we can move data basically every cycle. And actually, it might be easier if we just replace this with a counter for now. But anyway, so yeah, now we can move data every cycle. Let me just think, what is the next problem that we have with this circuit? Oh, I think I know what it is. Let's just start this from scratch. And in the meantime, I'm going to... There. So say we've got valid data, we've got a piece of data that we're going to move. We clock it. Then there's no more valid data coming in, and we've got a piece of data in this register. When we clock it again, it becomes invalid because we haven't accepted the data. That's bad because we want to hold the data in this register until the destination is ready for that data. We don't want to clear it out just because the destination didn't accept it. So otherwise we'll lose data, because this one is going to disappear if we get more data, right? So the one never made it to the destination, new data comes in, it gets clocked, and then we overwrite valid data that was sitting there waiting. That's bad. We don't want to do that. Otherwise, we'll lose the results of a pipeline stage, essentially. So we need a way to wait until the destination accepts its data before we move on, before we say that the data is no longer valid. So the easiest way to do that is just to add an AND gate. So this AND gate says if the data has not been accepted, oops, wrong knot. If the data has not been accepted and we've got valid data, need more room here. And we've got valid data, then we want to stay valid. We want to keep that data. So we'll need an OR gate right in here. So let me make room for that somehow. OR gate goes here. Or so we can set up that scenario here. So if we get valid data, clock it, the data is accepted, and then but the other side has not said that it's ready. So then now we'll just keep that data until it gets accepted. So valid is low. Now the other side is going to accept the data because it says it's ready. And it's moved into the destination now. Destination has accepted it. The valid signal goes low, and the transaction is complete. So that's an important piece. Let me just think what's next. I think those are the major parts. Yeah, that's the basic logic. It now should work in any situation. So let's say we've got valid data here, but we're not ready. It gets the data and it's valid. We signal that we're ready, but there's no more data. Valid goes low, but if there is data, then data basically transfers every cycle. So that is working correctly. So there's a few nice to haves on here. First of all, having the registers inside the control logic is kind of a no-go. So, well, actually, there's one more thing that we need to add. We need to add a way to clear it. Because occasionally what will end up happening is the data in the pipeline registers is invalid, say because we jumped to the wrong location and we need to clear the pipeline registers. So there's one more signal that we need to handle. We need to handle a clear, essentially. So now I'm not sure which side to put it on. I'll just put it here. This would be the clear. And if the, let's see. So if we're clearing, we want to make the data invalid, essentially. So in order to do that, I'm just going to move this over a little bit here. In order to do that, we need to be able to clear this line when the clear goes high, but we want to do it synchronously, so we don't need a asynchronous D flip-flop. We just need to clear it on the next cycle. Okay, I've never had this happen before, but I just lost a whole bunch of footage. I got quite a bit further along, and then I noticed, hey, wait a second, OBS is not updating. I'm glad it was here that it happened, but I think this is the same state it was in. Anyway, I was about to add this clear signal here. And then, yeah, everything just froze. Hopefully it doesn't happen again. So let's see. Yeah, so I'm just going to remove the boxes at that point, and then just move things over, move this up, and just kind of move things around to get it into the right spot. And here we go. So, yeah, I don't know if I should just redo it from memory or if I should just go through the undo buffer. I'm just going to go through the redo buffer. Yeah, I hope that's okay. So at this point, we've got a clear, and I don't want to mess up the undo buffer by running it, but you can trust me that this will work. We'll test it in just a second as soon as I get back through all of the work that I did here. So at this point, we've got a clear signal, and when that clear signal is high, it will inhibit any signal going into here and clear out this register. Now, there is a bug in this, in that currently we are able to set this register when the ready is not high. So I'm not sure how that happened, but somehow I missed that. So this AND gate needs to be on this OR gate here, and not directly from the valid signal on the input here. So I will fix that bug in a moment. First, what I'm going to do is essentially, this is just control logic. So in the control logic, we probably shouldn't have data with data registers and all of that. It would be nice if those were a separate circuit. So what I'm going to do is just remove those and convert the enable signals here to run to outputs. So then we can have external registers that are enabled by this circuit. So that's what I do next. I basically delete the whole top part here and change the input here. Well, this is an input. It should be an output. I'll fix that in a second. And then change this over here to be the destination enable. This is the source enable. I wire those up to the two AND gates. So then that's when data can be accepted. And then I just noticed that it was a input instead of an output. So then I just fixed that. And then this is where I noticed the bug where we shouldn't be accepting data if it's just valid. We should be looking at both of these signals being valid as the time that we basically store, because this register here represents that we've got data, valid data stored inside this pipeline stage, essentially. So then I fix that. And now I think I just clean up this circuit so that it's a little bit more tidy, so to speak. So I'm just moving things around a little bit here and tightening things up, and there. Okay, I think I'm at the redo buffer. So I'm at the same point as it was when OBS crashed. Okay, so the other thing that we need to do is this input, the data ready, destination ready. Quite often it goes to both the current pipeline stage as well as the next pipeline stage. And often you want to have an AND gate on that. So instead of having the AND gate outside of this circuit, I'd rather have it just inside this circuit. That way, it just makes it easier to use this circuit. I just said circuit a lot of times. So that's what I'm going to do now is just make 2 ready signals. So we've got 1 ready, and we'll just call it ready 1. And we've got ready 2. And we put that there. And then we move these over. Trying to think if there's anything else here. No, I think that's it. So now we've got a circuit that we can use to essentially control a pipeline stage. And it's got the basically a finite state machine in it. So we've got valid, and when this goes high, then this triggers the register to accept data at the clock pulse. And now we're in the state where we can test the clear logic. So we've got data stored in the register, and now for some reason we want to clear out the pipeline stage and reset it. And this could be totally used for reset as well. So then if this goes high, then in the next cycle, we basically forget the data that's in this pipeline stage. And occasionally that can be useful, specifically around jumps. If we don't predict the branch properly, which I don't know how sophisticated of branch prediction we'll have, we might actually get into that. We'll see. But if we don't predict the branch correctly, then the pipeline stages will be full of garbage data, essentially instructions that we shouldn't have been executing. So then we can use the clear to clear out that data and make sure that it doesn't cause problems. Now, I don't have this in my planning, but I'm wondering if clear is high, if we should be saying that we're not ready. That's a good point. Yeah, because we shouldn't be accepting data if we're going to just throw it out. No, I think we do want it to be thrown out. I think. Yeah, I'm not actually sure if we want to be discarding input data or not. I think I'm going to revisit this later when we know better how things are going to behave. So, yeah, I think I'm, well, this circuit is going to be called a handshake circuit, and handshake. And I'm going to, well, change these settings. And then I'm going to set it to layout here. Yeah, that height is probably fine. And I kind of just want to see what it looks like here, but we don't really have time to use it at this point. Yeah, that looks fine. Could probably be narrower by a little bit. Yeah, but otherwise that looks fine. Okay. So, I guess actually we've got, this is what we built this episode. So this is where the stuff goes. The scale is not right. All right. I think that's a wrap. Yeah. The FPGA CPU article will be linked in the description, as well as a link to the GitHub for this project. And I'd highly recommend grabbing this circuit and playing around with it, seeing how it would work in some pipeline stages, set up some pipelines and have some registers in between and see how it works in all of the different situations. I'd be very curious if you find some bugs. I suspect that this clear signal is going to come back to bite us. We'll have to do some extra logic on that. But otherwise, I've played around with this a fair amount and couldn't figure out any issues with it. Hopefully this has been understandable despite all of the technical issues with this. I just had it freeze yet again, so I don't know what's going on, but hopefully there'll be an update to OBS to fix that soon. Thank you very much for watching. There are links in the description if you're feeling generous. If not, that's totally okay. I hope you have a great day. Bye.